All right, so today we're going to talk about rational functions. So let's the other day when we talked about the rational root theorem, we talked about what a rational number was. Do you remember what a rational number was? Well, the root is ratio. So a rational number is a ratio of fraction. And what do we say a rational number was a fraction of?
A real number.
They are real, but they're special kind of real numbers. Integers. So a rational number is a ratio of integers, 3/5. Rational function, f of x, is a ratio of polynomials. And we also talked about how that is a D, yes. D as in denominator, M as in numerator, N of x and D of x. We also talked about how integers can be are made up of prime numbers. This is similar. We said polynomials, that the complex numbers are kind of like prime numbers for polynomials. So we're it's along the same idea. Rational functions, ratio of these polynomials that are made up of complex numbers. So we're taking a ratio of polynomials. And what we're interested in today is a couple of things about how they behave. So the first thing that we're interested in with any function is its domain. So since we have a fraction here, what's going to give us a problem in the domain? Dividing by 0, right? So our domain is anywhere where the denominator is not 0. And I want to contrast that because often students confuse the two. Our domain restrictions,
What does that say? Oh.
all x where d of x is not 0. Which one? Yeah, something was going on with my computer there, and it was really. All right, so our domain restrictions are where d of x does equal 0. So we're restricting from the domain the x values that make the denominator 0. Our domain is where the denominator is not 0, all those other values. So a lot of times when a problem asks for the domain, students will list the domain restrictions. Make sure you keep the two straight. We're also going to be interested in the x-intercepts. So for a function, how do we find the x-intercepts? What is true at the x-intercepts? Y is 0. So that is the same as saying f of x equals 0. And for a function that's a fraction like this, what is going to make this fraction 0? When the numerator is 0. So we're looking for where n of x equals 0. Well, n of x is a polynomial. Haven't we just spent several sections talking about finding zeros of polynomials? Yes, we have. So this entire unit is pretty much about finding zeros of polynomials. We're going to use finding zeros of polynomials to find our x-intercepts. We're going to restrict from the domain where the denominator is 0. We need to find the zeros of the denominator. Again, we're finding zeros of polynomials. How about the y-intercepts? What is true at the y-intercepts? X equals 0. So to find the y-intercepts, we plug in x equals 0. And we solve for y. So those are some important pieces of information about a rational function. Another important piece of information, the thing that I think makes rational functions most interesting. Does anybody remember what happens with rational functions? With their graphs? They can have holes, yes, and rational functions have asymptotes.
But the asymptotes are the x-intercepts of denominator.
One type of asymptote. And we'll talk about details with the asymptotes in a second. There are multiple kinds of asymptotes. All right. So I want to draw a couple of graphs, just sketch some graphs of some possibilities for what rational functions end up looking like. So I'm not going to write out what these rational functions are. I just want to sketch some possibilities for what they look like. So we could have asymptotes like so. And our rational function could look like this. Our graph could look like that. We could have a rational function that looks like this. We could have a rational function that looks like this. We could have a rational function that does something like this. Yeah, they can. This one goes through the dotted line too. This? No. So rational functions can have all kinds of these are just a couple of examples of the interesting shapes rational functions can have. What's that? The last one's pretty tricky. We won't have to do anything like that. But they do end up looking like that. So the first thing we want to do is we have an intuitive idea about what an asymptote is. I want to make that intuitive idea a little more solid. So we're going to define asymptotes. Our definition. We have two possibilities because we have vertical asymptotes and horizontal asymptotes. And there's actually another kind we'll talk about in a little bit. The line. Asymptotes are lines. The line x equals a is a vertical asymptote. Think I should yell at them? The line x equals a is a vertical asymptote if f of x approaches plus or minus infinity. as x approaches a. So what that's saying is, as we get close to this x value, the function gets really, really big negative or really, really big positive. Yes? No. Second part of the definition. The line y equals b is a horizontal asymptote. If f of x approaches b as x approaches plus or minus infinity. So vertical asymptote means our function is going up to positive infinity or going down to negative infinity. Horizontal asymptote means that our function, I'm going to draw a little picture here. And we'll say this is our horizontal asymptote. This is saying that eventually, as x gets really, really, really big, or really, 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 really small, really, really big negative, sorry, really, really big negative, that our function eventually gets close to that line. Eventually, my function gets close to this line. In between, so we're interested in what's happening here. In between, our function can do all kinds of stuff. We don't care.
Please.
All we're interested in is what happens as x gets really, really big this way, or x gets really, really big that way. Yes?
Keep drawing the lines passing the asymptotes, but we've been taught for the last 3 years that you can't cross it, so why?
No, we can't cross a vertical asymptote. We can cross a horizontal asymptote. All horizontal asymptotes tell us, listen, all horizontal asymptotes tell us is what happens eventually. It's not what happens in here, it's what happens out here.
That is great, because I don't think I've ever had a definition of that.
Yeah?
Yeah, thank you.
Yeah? All right, folks.
Is there no clear definition of what eventually means?
Yes, as x approaches plus or minus infinity. That's what eventually means. So a couple of other ways. Let's stop talking, folks, please. A couple of other ways that you might be asked about horizontal asymptotes. Horizontal asymptotes are about end behavior. You might be asked about the right and left-hand behavior. So we know for polynomials, our right and left-hand behavior are either they go this way, or they go this way, or they go this way, or they go this way. Well, rational functions eventually can approach a horizontal line, eventually get really close to a particular value of y. What I like to think about the horizontal asymptotes is what happens eventually. The horizontal asymptotes don't tell us anything about what's going on in here. All they tell us about is what happens as x gets really big or as x gets really small. How big or small? Plus or minus infinity. Now they can approach the asymptotes pretty closely for other smaller values of x, but as x gets close to plus or minus infinity, our function gets close to that asymptote. And we're going to connect this to our first calculus concept right at the end of the semester when we talk about limits. All right, so we want to know, how do we tell what kind of asymptotes a rational function has? Okay, let's quiet down please, folks. Thank you. So we need to talk about our asymptote rules. So our asymptote rules. So we have f of x equals n of x over d of x. Numerator and denominator. And I'm going to use an abbreviation. Degree of n of x. DEG is the degree. And DEG of d of x is the degree of the denominator. And degree just means the highest, whatever the highest power of the variable is. So if our polynomial is the highest power is a fifth power, it's a fifth degree. If our highest power is a seventh power, it's a seventh degree. All right, so we have the asymptote rules are really easy. The graph of f of x has a vertical asymptote. Add a line x equals a if the denominator is 0 at that particular value. And I'm going to put and n of a is not 0. We'll talk about what happens when they're 0 at the same time in just a second. So really what we're looking for is when the denominator equals 0. That's our kind of everyday way of thinking about how to find a vertical asymptote. Find where the denominator is 0. Those x values, we make a line, x equals whatever that is. Those are our vertical asymptotes. If our denominator is a fifth degree polynomial, we could have 5 vertical asymptotes. That would be a pretty complicated rational function. So we can have multiple vertical asymptotes everywhere the denominator is 0. We have only 2 possibilities for horizontal asymptotes. Has 1 or 0 horizontal asymptotes. And the reason for that is eventually our function can either approach some number or it can go to infinity. There are only 2 possibilities. Our function can't approach 2 different numbers as x gets really, really big. It can either approach 1 or it just keeps getting bigger and it doesn't approach any. The way we find those is we compare the degrees of the numerator and denominator. If the degree of the denominator is bigger than the degree of the numerator. So the denominator is bigger. Seventh degree power in the denominator, 2nd degree power in the numerator. Then the line y equals 0 is the horizontal asymptote. So that means that eventually our function gets closer and closer and closer to 0. We keep dividing by a bigger and bigger and bigger number. Our function gets smaller and smaller and smaller. Second condition, if the degrees are the same, then the line, and I'm going to write this in words, and then we'll write an example because it's easy to figure out. Then the line y equals the ratio of leading coefficients. Is the horizontal asymptote. So, for example, if I had f of x equals 9x to the third minus 2x squared plus x minus 1, and this is 7x cubed minus x plus 5. The leading coefficients, just like we found the leading coefficients for polynomials, the leading coefficients test, the numbers in front of the highest power of x. We're just interested in that, highest power of x. The ratio of leading coefficients, y equals 9/7, is the horizontal asymptote. So if the degrees are equal, you just pick out the numbers in front of the leading coefficients, and that's going to give us our value for our horizontal asymptote. If the degree of the numerator is bigger, so if the degree of the numerator is bigger, then there's no horizontal asymptote. And what that means is if the degree of the numerator is bigger, eventually the function just keeps getting bigger and bigger and bigger and bigger. So it goes to infinity. But I'm going to say there's another kind. There's a different kind. We'll talk about the different kind next time. It's not horizontal. There's a different kind. It can be slanted, yes. It could be a parabola. It could be a cubic function. It could be lots of different things. All we're doing is comparing. Which one is bigger? What's that? There's a different kind. There we go. All right, and then I want to go back to this thing where we said if the denominator is 0 and the numerator is not 0, if n of x and d of x equals 0 at the same time, there is a hole in the graph. How do we tell when the numerator and denominator are 0 at the same time? We could have something like this. X plus 1 times x plus 2 after we factor our numerator over x plus 1 times x minus 1. The numerator and denominator both equal 0 when x equals -1 because we have this factor in the numerator and denominator. So there is a hole when x equals -1 because the numerator and denominator are 0 at the same time. Yes?
Why isn't that just 0 over 0?
It is. So we're saying the function doesn't exist. But it doesn't exist in a special way. 0 over 0 does not necessarily mean infinity. We'll talk about that later on in the year. So this says the graph doesn't exist at that point. All right. So what I want to do is look at some examples of picking out vertical and horizontal asymptotes with rational functions. All right. So we're finding, for all of these, find the, I'm going to abbreviate it HA, VA, and holes. So on your quiz or test, when I write something, or on the test, when I write HA, I'm not laughing. I'm saying horizontal asymptote. No, I'm not laughing in writing. I'm not laughing in writing. If it's that bad, then I don't laugh. All right, so here's our function. F of x equals x plus 1 over x squared minus 1. When we work with rational functions, we should do exactly like we did when we did our partial fraction decomposition. We're going to factor the denominator. X plus 1, x minus 1. Because we need to know when the denominator is 0 for our vertical asymptotes. Well, what do we see right away here? We have a hole. Hole when x equals negative 1. Because the numerator and denominator are 0 at the same time. Our vertical asymptotes. Now, if there's a hole, the graph doesn't exist. So we can't have a vertical asymptote and a hole in the same place. So if it's a hole, it's just a hole. If it's a vertical asymptote, it's a vertical asymptote. So where's our vertical asymptote? X equals, we write the equation of a line. X equals 1. Because that makes this 0. No, at negative 1 we have a hole. If we have a hole, we can't have an asymptote and a hole at the same place. Our horizontal asymptote. How do the degrees of the numerator and denominator compare? Denominator is larger. What does that tell us? Horizontal asymptote at y equals 0, the line y equals 0. So if we sketched a graph, folks, we'll talk about how to sketch a graph later. I'm just going to show you what this graph looks like. We have a vertical asymptote at x equals 1, a horizontal asymptote at y equals 0, and this function turns out to look like this. And then we would go like so, except we have a little hole right there. That's when I said there's a different kind of asymptote, we can have a slant asymptote. And we would find the y coordinate of this hole by canceling out that x plus 1, and then we get f of x equals 1 over x minus 1, and plug in x equals 1 to, or x equals negative 1 to that. Yes?
How do you know which side the asymptotes both graphs
We'll talk about graphing these later, but basically what you have to do is plug in some numbers and plot a few points. All right, next one. All right, do we have any holes here? No. Is there a value of x that makes the numerator and denominator 0 at the same time? No. All right, how about a vertical asymptote? How do we figure it out? Vertical asymptote when how do we find the vertical asymptotes? When the denominator equals 0. So we'd say, we write the line x equals 6/4 or 3/2. Horizontal asymptote. The degree of the numerator and denominator are the same. So our horizontal asymptote is at the ratio of the leading coefficients, 2/4. The line y equals 1/2. And this rational function turns out to look like this. So that would be a graph of that rational function.
Is this going to be on the quiz?
No. Last one. X squared over x plus 1. Are there any holes? No. The numerator and denominator can't be 0 at the same time. Vertical asymptotes. X equals -1. Vertical asymptote is a line. You need to write the equation of a line. Horizontal asymptote. None, because the degree of the numerator is larger. No horizontal asymptote. This rational function turns out to look like this. So we end up with a slant asymptote. The numerator has a higher degree. So how are you going to guess that we're going to find that slant asymptote? What can we do when the numerator is bigger than the denominator? We can divide. We're going to find our slant asymptote by doing long division. We'll talk about that next time. Yeah, not next week, right? All right. I'm thinking we should probably redo all of this on Tuesday and then do the new stuff because we'll all forget it anyway. Yeah. All right. Before we talk about the homework, I have a question for you. What if you're told that a population is given by P of t, some population, is t to the third minus t squared plus 1 over t to the third, 2t to the third minus 4t plus 5. And it says what is the eventual population? What is that problem asking us about?
Oh, what's the horizontal asymptote?
This is asking what is the horizontal asymptote?
It's eventually going to be 1/2.
1/2 would be the eventual population. That would not be a good population model, right? Because you'd have half of something to be the population. I guess there could be pieces of candy left. So nobody wants to eat that last half piece of candy because you don't know who ate the other half, right? Yeah, no, I would never eat half a candy. I would eat the whole thing.